Okay, hello everyone. Can you hear me on Zoom?
Yes.
Okay, great. Sorry for the delay. The network was exceptionally slow this morning. Okay, we're going to begin talking about alkenes and alkynes today. Chapter 3 here. No, I'm sorry. I meant to do chapter 4. Okay. Bear with me. I'll need to close this file and open another one. Okay. Okay, as soon as that opens, I'll share my screen. Even taking a long time to open up a file. Okay, oh, there we go. All right, and I'm going to share my screen. All right, alkenes and alkynes. Alkenes and alkynes belong to a subset of the hydrocarbon family. They are called unsaturated hydrocarbons. And when we refer to saturated and unsaturated, we're talking about hydrogen. Okay, so alkenes and alkynes are deficient in hydrogen. The same terms are applied to fats, saturated and unsaturated fats. Saturated fats will have very few double bonds, whereas unsaturated fats will have a larger percentage of double bonds. Okay, we'll consider arenes in a separate chapter. Okay, these do not react like alkenes. Okay, even though we sometimes draw them like this with the double bonds. Let me back up for a minute. When a benzene ring is used as a substituent, it's called a phenyl. Okay, you'd think it would be called a benzyl, but it's called a phenyl. These are the representations of benzene as a substituent. Okay, ethylene, which is the simplest alkene, has a trigonoplanar geometry. All 6 atoms are in the same plane, and the bond angles are approximately 120 degrees. Okay, and then we have propene next to it. Okay, in propene, all 3 carbons and 3 of the hydrogens are in the same plane. Okay, according to the orbital overlap model, a double bond consists of 1 sigma bond, formed by the overlap of two sp2 hybrid orbitals and one pi bond formed by the parallel overlap of two p orbitals. Okay, so here we have the p orbitals. And when we have a pi bond, these will overlap side to side. And rotating about that bond will actually break the pi bond. Okay, in alkenes, we have what is called cis-trans or geometric isomerism. Okay, this is 2-butene. Butane, remember, is 4 carbons. Butene, the ending ene, indicates a double bond, and that double bond is located at 2. Okay, these are not constitutional isomers because the double bond is in the same place. The three-dimensional geometry in space is different. Okay, on the previous slide, we said that we couldn't rotate about this double bond. Okay, we actually have to break the bond, rotate, reform it. And so these are different compounds. Okay, this one is called cis, and this one is called trans. Let me zoom in just a little bit here. So this one is transparence. Okay, and then this one is transcendental. All right, now we'll introduce alkynes. The functional group of an alkyne involves a carbon-carbon triple bond. Okay, when you have a triple bond, you're going to have one sigma bond formed by the overlap. Instead of sp2, this time it's sp orbitals. The two pi bonds are formed by overlap of sets of parallel 2p orbitals. Okay, so an sp carbon, or sp anything, has a linear geometry. Okay, next we'll look at IUPAC nomenclature. The suffix is ene. If we have some other suffix, in other words, another functional group in addition to an alkene or alkyne, we'll use this infix, ene, and we'll come to examples of that. But we want to number the chain to give the first carbon of the double bond the lower number. Okay, we'll follow the IUPAC rules for numbering and naming substituents. For a cycloalkene, we'll number the atoms of the ring beginning with the 2 carbons of the double bond. Okay, so for example, okay, so here's an alkane. 1, 2, 3, 4, 5, 6. Okay, so that's hexane. And we want to give our methyl groups the lowest possible set of numbers. So we would want a number from this end. Okay, so that's 1, 2, 3. Okay, so this would be 2, 2, 3 trimethyl hexane. Okay, we're giving the substituents the lowest possible number. Okay. If, make sure this is still on screen. Okay, if we had a double bond, right, this time the double bond takes priority. Okay, so that means that this is number 1 and this is 2. Okay, so we would name this as 6 carbons. That's hexene. There's 2 ways of naming this. You call it 2-hexene or hex-2-ene. This is the more recent. But what this does, it locates the double bond. I'm sorry, that should be 1, not 2. Sorry about that. Okay, it's between 1 and 2. So 1-hexene or hex-1-ene. And then the other substituents will fall where they may. That's 2, 3, 4. Okay, so this is 4, 5, 5. Trimethyl. And then put a dash here. 4, 5, 5 trimethyl hex-1-ene or 1-hexene. Okay, double bond takes priority. For a cycloalkene, okay, we would, okay, as long as there's nothing higher priority, okay, we're going to cover functional groups in approximate order of ascending order of priority. If we have a cycloalkene, okay, we would call that cyclohexene. Okay, I actually don't need a number, okay, because no matter where I put the double bond, it's the same compound. If I do have other substituents, such as say we have something like that, okay, the double bond's automatically between 1 and 2. Okay, and we want to go this way to give these the lowest number. Okay, so this would be 3-ethyl, 3-methyl, cyclohexene. Okay, and it's understood that the double bond is between 1 and 2. And you can't change directions. We can't say, go this way and then, we have to be consistent in the direction that we're going. Okay, and again, we don't want to go around this way because that would be 1, 2, 3, 4, 5, 6. Okay, 6-ethyl, 6-methyl would not be correct. Okay, we want to give these the lowest numbers. All right, so these are some examples. We have 1-hexene, 6 carbons, double bonds between 1 and 2. 4-methyl 1-hexene. Okay, and then, okay, this one illustrates an important point, and that is, when we were talking about alkanes, okay, the parent is the longest chain, longest carbon chain. Okay, if we have a double bond, the parent is the longest chain that contains the double bond, that contains both carbons of the double bond. Okay, well, the longest chain is actually 1, 2, 3, 4, 5, 6. The longest chain that has both carbons of the double bond is actually 5. Okay, so the correct name is 2-ethyl, 3-methyl, 1-pentene. Okay, an alkyne will end in YNE. Okay, and again, the triple bond takes priority over the methyl. Okay, so the triple bond in this case is between 1 and 2. So this is 3-methyl, 1-butyne. Okay, we want to start here from the left. Okay, because that puts a triple bond between 3 and 4. If we go this way, it's 1, 2, 3. Okay, it'd be between 4 and 5. So we want to give the triple bond the lower number. So this is 6,6-dimethyl 3-heptine. Okay, 3 is where the triple bond is located. Some alkenes, particularly low molecular weight alkenes, are commonly, in some cases almost exclusively, at least in the United States, known by their common names. Okay, so the systematic name for the simplest alkene is ethene. Common name is ethylene. This is propene in the IUPAC, or propylene in the common name. This one is called isobutylene. Okay, remember isobutane. Okay, systematically it's 2-methylpropene. Okay, on the test, I'm just going to go by IUPAC. Both ethene and propene are commercially important. They're starting materials for plastics, polyethylene and polypropylene. Okay, thousands of these are linked together to form a long carbon chain. Polyethylene, you'd find that, for example, in plastic milk cartons, sandwich wrap, that's a branched polyethylene. Polypropylene, prescription pill bottles, yogurt, cottage cheese containers, for example, are made out of polypropylene. Ethylene is also a natural product which regulates fruit ripening. When fruit is shipped long distances across the country, picked when it's really green, and just before it's to be marketed, it's exposed to ethylene. There are also some commercial products on the market now. I think one of them is called green bags. You put your produce in one of those, and what it does is it absorbs the ethylene, and your produce will last longer because the ethylene will increase ripening. All right, so the alkyne functional group uses the suffix YNE. And again, we'll follow the IUPAC rules for numbering. Okay, we saw these earlier. Okay, cis and trans. Not every alkene will have cis and trans geometry. Okay, you have to have two different groups on both carbons of the alkene. Okay, here we have an ethyl and a hydrogen on both sides. Here we have an isopropyl and a methyl. On this side, we have a methyl and a hydrogen. Okay, so this is trans 3-hexene. This would be cis 3,4 dimethyl 2-pentene. Okay, so you indicate cis or trans just before the name. Okay, next we'll talk about E and Z. E and Z is actually a more precise method of identifying geometry. Okay, for example, okay, here I've got geometric isomers that have 4 different groups. Okay, these are clearly different. Would you all agree to that? They're clearly different geometric isomers. Okay, we cannot line up all the groups at the same time. In order to go from here to here, I've got to break this double bond, rotate it, reform it, or I've got to break this bond, and then switch these two. Okay, so these are different isomers. Okay, since we have so many different groups, 4 different groups, it becomes unclear which one is cis and which is trans. Okay. If I were to ask you which one is cis and which one's trans, it would be hard to do. Okay, but they're clearly different. Okay, so the E and Z method of designating geometric isomers can also be applied to cis and trans. And as I say, this is a more precise definition, or more precise designation. Okay, E and Z come from 2 German words. Z is zusammen, which means together. E is entgegen, which means opposite. Okay, so what we do is we prioritize these groups based on atomic number. Okay, so we'll compare these 2 groups over here, bromine and chlorine. Bromine is atomic number 35, chlorine is 17. All right, so bromine wins out. Okay, what about carbon versus hydrogen? Carbon, yeah. Carbon has the higher priority. Okay, priorities are the same here. Okay, so we compare the 2 that are on the same carbon. We set priorities. All right, in this one, the 2 higher priority groups are on Z same side. So that's a Z. 2 higher priority groups are on Z same side. Okay, and then this one would be the E because they're opposite. Okay, so here we have some examples. The higher the atomic number, the higher the priority. Okay, and here's some examples of atoms that are directly bonded. Okay, and what if the groups are the same, but, I'm sorry, the groups are different, but the atomic number that is bonded Okay, an ethyl and a CH2OH group are different. Okay, this one, we just did this, so this is, we know that carbon takes priority over hydrogen. Okay, when we're comparing priorities, we compare the first one, then we compare the second one, and we keep going until we find a difference. Okay, so for this one, I get some colored chalk here. Okay, carbon and carbon are the same. Okay, so we work our way up to the next one. In this case, it's carbon versus oxygen. Okay, carbon's atomic number 6, oxygen is atomic number 8, so oxygen is the winner. All right, so this would be Z. Okay, the two higher priority groups are on Z same side. Okay, in order to make it E, okay, I would switch either these two or I would switch these two. Okay, here's a good example down here at the bottom. We have CH2OH and then we have CH2Cl. Okay, chlorine takes priority over oxygen. Okay, oxygen takes priority over nitrogen. Okay, what if we have a double or triple bond? Okay, let's say we have okay, let's say we have something like this. Okay, again, we have carbons as our first atom. The next one out is a carbon. Okay, we treat a carbon-carbon double bond like it's bonded to two carbons. Okay. So if I were to write these out, yeah. Okay, we've got carbon and carbon are the same. Hydrogen, hydrogen are the same. But then we've got one carbon and one hydrogen versus we treat this as though it's two carbons. Okay, so this would take priority. All right, if we had a CO double bond, okay, for example, okay, carbon and carbon are the same. Next one out is an oxygen, but we would treat this like it's two oxygens. Okay, so this would take priority over that. Okay, in a case like this, as soon as we find a difference, then we stop. We ignore everything else. Okay, we don't go by molecular weight of the group or anything like that. Okay, so this is carbon, carbon. Okay, then it's carbon versus oxygen. Okay, we're done. Okay, the rest of it doesn't matter. Okay, as soon as we find a difference, we stop. If we have another common one that we encounter is a CN triple bond. Okay, we would count that as though it were 3 nitrogens bonded to our carbon. Okay. All right, so let's work these. Okay, your choice is E or Z. Okay, for part A, what do you think? Okay, E is correct, right. Okay, on the right side, as I find my cursor there, carbon and carbon are the same. The next one out is a hydrogen versus a carbon. So ethyl beats methyl. So ethyl wins out over methyl. So that's your higher priority group. Here, carbon and carbon is the same. Next one out is a hydrogen versus a chlorine. We follow the pathway that most quickly gives us the difference. So that would be E. What about B? Okay, there's a hydrogen here that's implied. What do you think? Z. Yeah, Z is correct. Okay, bromine has a higher atomic number than chlorine. Okay, let's look at C. Okay, we have a methyl versus an isopropyl. Okay, which one is higher priority? Isopropyl is higher priority. And then we have a methyl versus a propyl. Okay, so the 2 higher priority groups are opposite, so that would be E, right. Okay. And again, with this one, we have a hydrogen here that's implied. Okay, so the propyl takes priority over the hydrogen. Here, the first atom in both groups is a carbon. We have 2 hydrogens and a carbon that's bonded to it. Here we have 2 carbons and a hydrogen. Okay, so the cyclopentane would take priority over the ethyl. Okay, so this would be, again, this would be E. All right, the configuration of the double bond in cyclopropene through cycloheptene must be cis. Okay, so a small ring up to 7 carbons, the double bond has to be cis. Cyclooctene is the smallest cycloalkene that can accommodate a trans double bond. Okay, even then, it's only marginally stable. Okay, if you look at cyclohexene or cyclopentene, okay, I think it's fairly easy to tell that this is cis. To make a trans double bond, you couldn't even do it with these models. Okay, so at least 8 carbons in your ring. All right, if we have a compound with more than 1 double bond, if it has 2 double bonds, it's called a diene. Okay, and we need to specify the positions of both double bonds. Okay, so in this first example, this is trans-trans. Okay, both the double bonds are trans. 2,4-heptadiene. Okay, diene, 2 double bonds, and they're at 2 and 4. This would be trans-cis. Okay, we can also name it like this. The first one, the one on the left, we could call that, we call it 2E, 4E, 2,4 heptadiene. Okay, these may seem kind of redundant, but you do need to indicate the numbers both here and here. Okay, and then the other one would be 2. Let's see, it would be 2E, 4Z. Okay, so you could also designate it like this. Okay, vitamin A, which is also called retinol, has 5 double bonds, 4 of which can show cis-trans isomerism. Okay, not every double bond can be cis or trans. Okay, and this shows the oxidation that takes place where the alcohol is converted into an aldehyde. This is vitamin A aldehyde, also called retinal. Okay, and the vitamin A isomer is the all trans. All the double bonds are trans. I'll mention this briefly. We're just about out of time. Sorry about the late start today. Okay, so alkenes and alkynes are non-polar compounds, a lot like alkanes. Okay, the only attractive forces are London dispersion forces. Okay, they don't hydrogen bond, they don't have dipole-dipole forces or anything like that. And so the physical properties are similar. Similar boiling points, similar solubilities, and like alkenes and alkynes are insoluble in water. All right, so I'm going to go ahead and stop there, and we'll pick this up again on Wednesday.